Swayam Prabha. Digital India. Educated India.
Okay, hello everyone. We will continue our discussion on integers in this video, and we have learnt about GCD and a very important result known as Bijou's theorem as stated here, which says that given two integers a and b, their GCD has an expression of this form Ra plus Sb, some integer times a plus some integer times b, but these integers can be positive or negative. Now that result is very strong result, and it can be used to prove some very important other results. So let us see this. One particular lemma says if D is a common divisor of A and B, then D divides GCD of A and B. This directly follows from the proof of Bijou's theorem, because we have seen that the GCD has an expression of the form n times A plus m times B, and because any common divisor divides both A and B, it divides this also, so that it divides the GCD also. So this is obvious from Bijou's theorem. Now Euclid's lemma is also a very important simple lemma, which says that if P is a prime number and P divides the product of two integers a and b, that is P divides AB, then either P divides A or P divides B. P must divide one of them. So to prove this, let us suppose P divides AB, but P does not divide A. If it divides A, then there is nothing to prove. If it does not divide A, then we will prove that P must divide B. So because it does not divide A and P is a prime number, the GCD of P and A must be 1. Right? Because no other, the only divisors of P, the positive divisors of P are 1 and P only, and then P does not divide A, so the GCD must be 1. So if the GCD is 1, using Bijou's theorem, we say that one can write 1 is equal to some integer times P plus some integer times A. Right? GCD is equal to Rp plus SA. Now we multiply B on both sides, and what do we get? Rp times B plus SAB is equal to B. Now if we see, let us divide by P both sides and see what we get. This term AB is divisible by P by assumption. Now this is also divisible by P because P is there as a factor. So the left hand side is divisible by P. So the right hand side must also be divisible by P, and that means P divides B. So that proves the result. Now this is a very important result here, which is called by different names. One is unique factorization theorem, and another popular name is fundamental theorem of arithmetic. It says that any positive integer can be factored in a unique way as a equal to p1 times p1 power alpha 1 up to pt power alpha t, where p1 and pt are prime numbers arranged in descending order. The descending order, this is insisted on just to make this unique, otherwise one can say up to ordering this is unique. So these are prime numbers in the descending order, and each alpha I is greater than 0. Okay. So we know this because we know how, given any prime any integer, how to get prime factorization, right? You do, suppose if you have 48, you first take the smallest prime number which divides it 2, so then you get 24, you get again 2, 12, 2, 6, 2, 3. So you have 48 is equal to 2 power 4 times 3. So this is the unique prime factorization. Or in this form, if you want to write in this order, then it will be 3 times 2 power 4. That is all it says. Now for the proof, see many books will have the proof. For example, Topics in Algebra by Herstein, it is a very popular book on algebra. Now another thing that we will now study is congruence modulo an integer n. An integer n is taken, and then we say that two integers a and b are congruent modulo n if n divides the difference of a and b. So, and we say in words that a is congruent to b modulo 5 and write it this way. We can check that this is an equivalence relation, and the equivalence classes are how many equivalence classes are there? Exactly n equivalence classes corresponding to the possible remainders after dividing by n. So, how many possible remainders can we get if we divide any integer by n? We can get remainder 0, remainder 1, remainder 2 up to remainder n minus 1. So, we will get remainder 0 for a set of integers, and those form one equivalence class of this relation. It is also called the congruence class modulo n, right. Congruence class modulo n. This is one congruence class, this is another congruence class whose remainder is 1, and this is another whose remainder is n minus 1. The smallest positive representative of this set is 0. Smallest positive representative of this set is 1, and smallest positive element in this set is n minus 1. And so these are usually taken as the representatives of these sets, and these equivalence classes or congruence classes are denoted by either this symbol or this symbol. This notation may vary from book to book, but they are expressed in terms of those smallest positive elements in the corresponding congruence class. Now we take the set of these congruence classes. This is basically the residue class that we have defined before under any equivalence relation. This is the set of equivalence classes. One can also define an operation between or addition between these equivalence classes or congruence classes. The addition is defined as I plus j, the equivalence class I plus equivalence class j is the equivalence class of I plus j. Similarly, multiplication can be defined. Now, there is whenever we define something like this, we need to be careful, because this is a set and this has many elements. This I here happens to be one of the representatives that is taken from that set, and that is used in the definition of the right hand side. But what if you take another representative in the same congruence class? That should also give us the same set here, otherwise this definition is not meaningful, not well defined, we say. So we need to prove that this is the way we have defined addition and multiplication of these congruence classes is well defined. Okay. So for example, for the addition, we can take any other element in this, take I plus an. Okay. So I plus an also belongs to the same congruence class, and that means this you can also write as I plus an. So, if you take I plus a n instead of I here, and you are taking the same congruence class, but just writing it differently. Similarly, j plus b n, and then if you take these two representatives, your addition here would be I plus j plus a n plus b n. Is this same as this set? We need to check. If they are not the same, then there is a problem in the definition, because it then depends on which representative you are taking here to define it. So, if you see now, of course, this is also same as I plus j, because this part is divisible by n. So, as a result, you say that this representative, which representative you have taken here to define this set right hand side does not matter, you get the same right hand side anyway. So, it is well defined. Similarly, one can also check that this definition of multiplication is also well defined. Okay, now we will discuss about maps and define certain types of maps, and also discuss some related definitions, and then discuss some basic results about maps. So, first of all, what is a map? A map is a relation actually. So, when you say F is a map from A to B, we mean that, so A and B are two sets, we mean that it is a relation of A into B. That means, it is a subset of A cross B, but not all relations are maps. Those relations which has the following property are called maps. The property is that for every element A in capital A, there is exactly one element in B which we denote by f of A, with which it is related. That means, this is in the relation. Okay. So, it says two things. One is that for every element in A, there is at least one element in B, but not only at least. The second thing is that it is unique. There is exactly one element in B to which it is related. Such relations are called maps. So, A is called the domain of the map, and the set of all f of A, set of all elements in B to which some element in A is related to, right, is called the codomain. The codomain or range or image. And this is a subset of B. Okay. Now, if, so this is, you can visualize it is like this is A, this is B, there is a map F, and this whole set may be mapped to a subset of B, which is the image of F. Okay, this subset is the image of B. Outside, for these elements outside here, there is no element to which it is related to. Okay, so, it is not in the image. So, now it may happen that two elements in A map to the same element, right? They go to the same element, and then that is not that. So, when that does not happen, that is every element goes to a unique element, separate element, okay, distinct elements, then such a map is called one-to-one map or injective map. Right. And sometimes I mean, we also say that map is an injection. So, one-to-one map or injection or injective map. Okay. Now, as I said, the image of F need not be equal to the whole set B, but if it is equal, then such maps are called onto map or surjective map. Okay. This is when for every B in B, there exists an A such that B is equal to f of A. If this happens, then we say this is an onto map or surjective map or a surjection. If both these hold for a map, then we say that this is a one-to-one correspondence or a bijective map or simply a bijection. Okay. So, bijective map is a map which is both injective and surjective. Okay. Now, for any element in the image, any element say for any B in B, f inverse of B, it is called the inverse image of B or pre-image of B or the fiber of B. It is the set of all A for which A in A, for which f of A is equal to B. So, this is basically there is B here and the set of all elements which goes to B, this is the f inverse B. Now, note that this f inverse does not denote the inverse map, because it is not a map. Okay. There are many elements in the f inverse of B, unlike an inverse map which will, in which case it will mean that this is a single element in A, singleton in A. So, indeed when this is a singleton for every B, the set is this is a set, and if this set is a singleton in B, then f inverse defines an inverse map. Now, a special map which takes every element of A to itself. So, it is a map of A to A itself, so that every element A goes to A. Okay. It does not do anything basically. So, then that map is called the identity map. Okay, ID A. And if you have a subset of A, for any map A to from A to B, if you have a subset C here, then clearly this map also defines a map from C to B. You just restrict F to C, which means that so F is A to B, but its restriction, which is denoted by F restricted to C like this, it is a map from C to B, but the definition of the map is the same. So, take any element C, small c, it goes to f of C. F of C is defined because C is also an element of A, it is here as well. So, this map is defined for that element. So, such a map is called the restriction of the map F on the set C. Now, when you have a subset C here, you can also define a map of C into A, map from C to A, which again is the identity map. Right. So, that is so basically it is viewing an element of C as an element of A, and that is called the inclusion map, or so it is called the inclusion map here. Now, if we have two maps, let us say one from A to B, you have one map from A to B, another map from B to C, this is F, this is G. Then we define G composition F, this is the map from A to C. How is it defined? It is basically if you take any element A, G composition F, this map of A is defined as, you first take f of A, right, this A, you take f of A, it goes somewhere here, f of A, and then this goes somewhere here, which is by G. So, that is G of f of A. So, G of f of A, this is the definition of the map composition G composition F, right. Now, if there is a map F from A to B, F, and there is a map from B to A, let us say G, then one can ask, what if you compose G with F? So, G composition F, it is a map of A, map from A to A, and if this map is identity map, if G composition F is the identity map of A, then G is called the left inverse of F, and F is called the right inverse of G. Okay. So, F is called the right inverse of G and G is called the left inverse of F. Now, this does not necessarily mean that G is the inverse of F as we know. Okay. Why? Because it may happen that B is a bigger set than A, and I mean that is one example for finite sets, where and A, this is a one-to-one map, F takes every element to a unique element here, it is a different element, distinct elements, and then G takes them back to those same elements, but outside the image there is no guarantee. Outside the elements, this element may be taken to an element here, which is also the image of this map, this image, this element here. So, G need not be one to one, and F or may not be onto in this example that I am showing. So, even then G composition F is still an identity, still the identity map. G composition F of A is same as A itself for every element A in A. Okay. But there B, G, so but F may not be onto and G may not be one to one. Okay. Now, left inverse exists if and only if F is a one to one map. As I demonstrated here, if there is a one to one map, F is one to one, then you can define the G such that, so F takes every element to distinct element, right, and this is the image. So, what we can do is we can define a map which takes the image to back to the corresponding element here, but outside you can map anyhow you want, any way you want. Okay. So, that if you define G in such a way, then G composition F will be identity map. Okay. So, as long as F is one to one, we can define G that way. So, we can construct a left inverse of F if F is one to one, whereas if it is onto, then we can define right inverse, just like for G. Suppose now you take G, G is onto, so it takes it is its image is full A, then we can always for every element here, it's take the set of elements which are taken to that element by G, select one of them and define that to be f of a, define that to be f of a. So, because it is G is on to every element here, you are defining a corresponding element in B, okay. Then what will happen is that that F composition G will be the identity map, and these pre images are disjoint. This is by definition, because by the very definition of G, two elements here cannot have the same image under G. So, what we have argued here is that because if G is onto, this implies that there exists F such that G composition F is identity map. Here first we showed that if F is 1 to 1, then this implies there exists G such that G composition F is identity. So, which means that if F is 1 to 1, then there is a left inverse of F, and here we have shown that if G is onto, then it has a right inverse, F is the right inverse of G. Okay. Now, we will discuss some basic results on maps. You can find some of these results in two standard books on algebra. This is a very popular first book on algebra, Topics in Algebra by Herstein, and this is Algebra by Hungerford. So, this result says that the composition operation between maps is associative. So, if you have three maps, sigma from S to T. So, if you have sigma from S to T and then T to U and U to V, you have three maps, sigma, tau, mu, right. So, if you take tau composition sigma, so that becomes a map from S to tau composition sigma, that becomes a map from S to U, then you can again further take mu. So, that gives you mu, mu composition tau composition sigma. Now, you can take composition of tau and mu first, and then so you have a T to V map, which is mu composition tau, and then you have a map from S to T, which is sigma. So, their composition will be mu composition tau composition sigma. So, both these are maps from S to V, S to V, S to V, and both these are the same. So, order in which we take the composition operation does not matter. Okay. So, this is the this so called associativity property, and we will not do the proof. The proof is very simple, and I leave that as an exercise. You basically compute both sides on a particular, you take any S here in capital S and just compute the left hand side and right hand side, and then you can show that you will get the same element. Now, this is lemma 2. It says that if sigma is a map from S to T and tau is a map from T to U, then if both these maps are onto, then their composition is also onto. If this is onto, then the composition of tau composition sigma is also onto. Why is that? Because every element in U has an element here. So, the tau of this element is this chosen element u, and because tau is onto, and then because sigma is onto, there is an element here in S which goes to this element and which then tau takes to u. So, the composition tau composition sigma takes this element in S to this element. Okay. So, every u has a pre-image like that. Now, similarly, one can also show that if both are 1 to 1, then their composition is also 1 to 1, because 1 to 1 mapping means if sigma is 1 to 1, then any two distinct elements in S go to distinct elements in T. And similarly, because tau is 1 to 1, these two distinct elements go to distinct elements in U. So, their composition is also 1 to 1. Now, if S is a finite set, then 1 to 1 and on to are the same thing. Why? Because 1 to 1, okay. So, S is a finite set and a map sigma from S to S itself. Okay. So, we are taking that type of map, S to S map, and S is a finite set. Then let us see if it is a 1 to 1, then so suppose S has a finite number of elements, let us say 100 elements here, and so if every element here goes to distinct element here, then the image of F will also have 100 elements, and the whole of S has 100 elements here. So, all the elements must be in the image. So, that means F is onto. Similarly, if F is onto, then every element here has a pre-image, okay, and there are 100 elements whose image is this 100 elements here. So, if two elements here went to the same element here, there must be one element here in the in this place which is left out. Okay. So, it would not be onto if it was not 1 to 1. So, that is what it means that 1 to 1, F is 1 to 1 if and only if F is onto. This is not true for an infinite set. So, let us see an example. Suppose you take the set of integers z, and take this map which is multiplication by 2. Okay. So, every element here goes to 2i, I goes to 2i, this map. Now, clearly, this is on to map, this is 1 to 1 map, because when you multiply two different elements by 2, you get again two different elements. 2 times two different elements cannot be the same. So, it is 1 to 1, this is 1 to 1, but is it on to? Clearly not, because the image is exactly the set of all even numbers here. The odd numbers are not in the image. So, it is a 1 to 1 map, but not on to. And yeah, okay. Now, we talked about 1 to 1 correspondence. 1 to 1 correspondence means it is a 1 to 1 and on to map, as injective as well as surjective. So, it is a bijective map. If you take the set of all such maps, this is denoted by this A of S, and this is a very important set, as we will discuss later also. The set of all bijections or 1 to 1 correspondences in S. Under composition, they have very nice structure which is called, the group structure that we will see later. Now, one thing we will note here is that this set composition is not a commutative operation in this set. So, what do you mean by that? So, these are maps from S to S, right, S to S. Now, if you have two maps F and G, you can take G composition F here, because G can be also thought as a map from this to this side. because the sets are the same, right. So, G composition F and same as similarly F composition G are also defined. Okay. Now, these two need not be the same in general, and let us see an example. So, if S is greater than 2, the number of elements in S is greater than 2, then this composition operation is not commutative. Okay. So, let us take an example. Suppose we take let us say 1, 2 and 3 are there in S, okay, and there may be more elements and it does not matter. So, we will take a map which takes 1 to 2, 2 to 3 and 3 to 1. Okay. So, now we will take a map which takes just 1 to 2 and all other elements fixed, all other elements fixed. This is simpler, all other elements are fixed, and we will take another map. So, this is sigma, and another map which takes 2 to 3, this is tau. Now, do these two and all other elements are fixed, they do not change, right. So, which means that tau of this element is itself for all other elements other than 2 and 3. So, now let us see what is tau composition sigma. First you apply sigma and then you apply tau. So, what happens? You first apply sigma, then 1 goes to 2 and then you apply tau, 2 goes to 3. So, 1 goes to 3 by the composition map tau composition sigma. What happens to 2? 2 is sigma. So, 1 goes to 2, 2 goes to 1. Okay, this is the map. I did not completely specify, now I specified it. And so, sigma takes 2 to 1 and tau does not change 1, it takes to 1 itself. So, 2 goes to 1, 2 goes to 1. Okay. Now, what happens to 3? 3 is fixed by sigma, but then tau takes it to 2. So, 3 goes to 2. This is the composition tau composition sigma. Now, let us compute sigma composition tau and see what we get. Sigma composition tau, first apply tau then sigma. So, first apply tau, then 2 goes to, so 1 does not go anywhere. If you apply tau 1, 2, 3, right. So, and we are drawing sigma composition tau. So, we apply tau to 1, it does not change, it is 1, and then sigma takes it to 2. And then if you see where does 2 go to? 2 goes to 3 by tau and then 3 is not changed by sigma. So, it goes to 3 like this. Now, what happens to 3? Tau takes it to 2 and then sigma takes it to 1. So, 3 goes to 1. This is sigma composition tau, and you see that these two are quite different maps. These two are different maps, sigma composition tau and tau composition sigma. So, it does not matter if how many other elements are there, all it needs is that there are 3 elements at least in S. Then there exist 2 maps sigma and tau we have shown, such that they do not commute with each other, which means sigma composition tau and tau composition sigma are different. Now, this is something that we have actually proved already one part of it. If F is a map from A to B and A is not empty, then if F is injective, we have argued before that there is a left inverse of G. Similarly, if F is surjective, then there is a right inverse of F, left inverse G and right inverse H if it is onto. Now, one can also see that the other way is also true. That is, if there is a left inverse, then f must be injective, if there is a right inverse, f must be surjective. Well, why is this? Because let us take the first one, the second one is also very simple. So, if we are given that G f or G composition f, which is often sometimes just written as G f, this we know that this of A is G of f of A. This is same as A itself, because it is same as the identity map. Now, if it is A itself, then clearly f has to be injective, because if you have two elements A and A prime, if A and Fa and Fa prime are the same, then G of them also will be the same. G is a map, it takes one element to only one element. So, if these two are the same, then G of these two will also be the same, but we know that this is equal to A and this is equal to A prime, and they are distinct, they are different elements. So, this will be a contradiction. Okay. So, Fa and Fa prime cannot be different, cannot be the same if f is if this is true, if G composition f is the identity map. Now, here we have suddenly changed this notation, composition we have not written this circle. So, this is because often the composition is viewed as a multiplication operation. Whenever an operation is commutative, we mentally think of it as addition, we sometimes call it addition also. Whenever it is not commutative, we think of it as a multiplication, because we are used to thinking of multiplication as a non-commutative operation, but not so for addition, because we know instances of multiplication operation which are not commutative. For example, matrix multiplication. So, they are just written side by side to mean that this is multiplication, or in this particular case it actually means composition. So, it is same as this. Okay. This is almost the same as what we have said in this. It says that a mapping sigma of from S to T is a one-to-one correspondence. Now, this is bijective if and only if there is a inverse of that map. Okay. There is a mu which is both a right inverse and left inverse of sigma. Okay. So, we know that if sigma is 1 to 1, then there is a left inverse, and if sigma is on to, then there is a right inverse. But now we are saying slightly more than that, that there is a single map which is both the left inverse and right inverse of that map. Now, this is also easy to see, because it is one-to-one correspondence. If it is a one-to-one correspondence, there is exactly one element in T to which every element here is mapped to. Every element here has a exactly one element here, and no other element here is also mapped to this. So, you can just define for this element this map to be that. Okay. It is on to, so there is an element here in S which is taken to T. For every T there is an element S whose sigma of which is T, but there is a unique element in S whose image is T, because it is 1 to 1. Okay. So, we define mu of T to be that unique element in S. Then it is easy to check that this is the thing, and similarly one can also check the other way. It is quite easy, and we will leave it as an exercise for you to do offline.